What the heck?
Tagon.
And we're back. First video in quite a long time. So to anyone that's watching that gives a rat's ass, I've just been a bit busy with doing other things, job searching, and life in general. These next videos are just going to be me showcasing a couple of ideas that I've had that I'd like to share, that I think are mathematically interesting. I don't know exactly how far we can take these things, and that's what I'm doing here. I'm posing this question to the few that do watch my videos, and so we're going to see what we can derive together. This will just be sort of an introduction of one of these ideas, and over the next couple of videos we'll sort of elucidate the others. I guess new ways of looking at problems that I've come up with that I think are interesting to try and solve is generalizing the idea of integrating inverse functions, which is what we're going to do today. So a general formula for, say, the nth integral of a particular inverse function, assuming we know certain things about the original function. Another thing is studying the ideas of small and large sets, which are collections of natural numbers. They're small if the sum of their reciprocals is finite. It's a large set if the sum of the reciprocals diverges. And I had a neat way of looking at that I'd like to talk about and maybe shed some light on that subject. Then there's the idea that I had of perpendicular functions, which is like generalizing the idea of perpendicular lines to functions that have derivatives that are the negative reciprocal of everywhere of some other function. And so no matter how you move the other function up and down, it always intersects the original function at a right angle. There are some interesting results there. And then another idea I had was the idea of generalizing trigonometric functions. Now, when I say generalizing trig functions, I mean in the sense of considering them as rational expressions in the variable e to the ix. And if that's not immediately clear to you what I mean by that, then we'll talk about it when we get to that video. But for today, we're doing integrals of inverse functions, and we're going to see a general formula that I've been able to find, and we're going to see some neat results that we get from that. And I look forward to hearing what anybody in the comments or through email has to expand on this idea, or expound on this idea, I should perhaps say. So let's get started. It's been quite a while. I'm excited to get back into the math. So we want to generalize the idea of integrating an inverse function. So let's first of all talk about what we know about inverse functions and their relationships to calculus. So we know that let's say we are given some function f of x, and for the sake of just talking about all of these neat properties, we're going to say we know its derivative as well, and we're going to say we know its antiderivative, capital F of x, so the derivative of capital F of x is just regular f of x. We have learned in a video that I've made before that the derivative of inverse functions can simply be written as the reciprocal of the derivative of the original function applied to the inverse function. So another way to write that is as the composition. So 1 over f inverse composed with the derivative of f at x. So this is the derivative of an inverse function, and we were also able to derive, kind of a funny word to use in this context, the antiderivative of an inverse function, and that turned out to be x times that same inverse function minus the antiderivative of f applied to the inverse function plus a constant. Again, you could rewrite this as a composition of two functions. So kind of not surprisingly, if in the derivative of the inverse we need to know the derivative of the original function, then in the antiderivative of the inverse we should need to know the antiderivative of the original function. So that's not too surprising. And although I've tried to come up with a general formula for, as you know, repeated derivatives of the inverse function, I seem to get sort of wrapped up in all of these symbols that I can't make too much sense of. And I'm having trouble finding a general formula. So if anybody would like to give that a shot, I would really love to see an answer. But what we're going to showcase today is a general formula for repeated integration of an inverse function. And for the purposes of this video, we're going to ignore the constant that we get from integration. So we're going to assume that for the sake of simplicity, whatever function we have, the constant we get after each integration is going to be equal to 0. Just for the sake of simplicity. Perhaps if there's a more detailed investigation of these things, one could perhaps see how the constant will affect the answer in the end. So let's get right to the formula. So essentially I derived this formula through trial and error. I essentially just took this answer for the first integral, integrated that, did that multiple times until I started to see a pattern in the coefficients of the terms that we got, that I would get in the process. And then I sort of just took a guess at the answer and then proved it with induction. And that's exactly what I'm going to do for you today, except we're going to skip right to the answer. We're not going to do any of the hard stuff in between. If you'd like to see that, perhaps I could work it out, but there's still a lot to see beyond just the answer. So I'm gonna have to introduce you to some notation. So we don't need to know the derivatives of f in this case, so let's again just say we are given f of x, and we also want to be given another class of functions, which is, so it's like sort of a sequence of functions. So a sequence of functions f, capital F sub m of x. So this is a function we're being given. This is a sequence of functions where the derivative of each of the fm's, the big fm's, is precisely the original f of x to the power of m. So we're going to need to know these antiderivatives. We're going to need to know the antiderivatives of f to the power of m if we want to be able to integrate the inverse function m times, or however many times. I'm just going to use the letter n actually, because that's going to be the one we're going to use as our input. And so, we need to know quite a bit. I would imagine a similar aspect to the derivatives would be if you wanted to know the nth derivative of the inverse function, you would need to know the nth derivative. You would need to know the derivative of the nth power of f of x if I had to take a guess, but I'm simply not sure. I know that you need this for this process. And we're also going to say that the symbol phi n, which is a function of x, phi n of x, I'm going to assume it's a function of x, and I'm just simply not going to write that part. This is going to be defined to be the nth integral of f inverse of x. So this is, integrate once, then again, then again. And as it turns out, this can be written in a closed form. It just requires n terms, so a sum from 1 to n, from 0 to n actually, so I guess n plus 1 terms. But it's a closed form expression. We want phi 0 to be no integrals of the inverse function, so just the inverse function on its own. And in this formula, you're going to see me write phi 0 representing the f inverse function, just to sort of have some consistency. And of course, whatever formula we end up with, we want phi 1 to be that thing we already know, x times f inverse of x minus the antiderivative of f applied to f inverse of x. So we know we definitely want these two things, but more importantly, as a general rule, we want the derivative of the nth phi to be equal to the n minus first phi, right? That's important because we're saying that phi n is the nth integral of f inverse. So we want to be able to take n derivatives and get right back down to f inverse. So these things all have to be true about our answer, and I will tell you the answer now, and then I will prove it to you using induction. So as it turns out, phi n, the nth integral of f inverse, can be expressed as this sum. The sum from m equals 0 to n of negative 1 to the power of m times x to the n minus m all over m factorial times n minus m factorial times these integrals of the powers of f, but applied to the inverse function. So that is quite a mouthful, but I can prove it to you using induction. All I have to do is prove the base case and then show to you that the derivative of any of these is the one before it, which means we can always work backwards, right? So let's prove it. So is phi of 0 the inverse function? Well, let's see. If we plug in 0 equals, or n equals 0, we're going to have a sum from 0 to 0, so there's only going to be one term, which means phi of 0 is going to be negative 1 to the power of 0 times x to the power of 0 minus 0 all over 0 factorial times 0 minus 0 factorial times f sub 0 of f inverse of x. Well, negative 1 to the power of 0 is 1, x to the 0 minus 0 is 1, 0 factorial is 1, and again 0 factorial is 1. So all of this is 1. Right? That's easy. But now, what's this? What would big F0 be? Well, big F0, the derivative of big F0 is going to be f of x to the power of 0. But f of x to the power of 0 is just 1 which means the derivative of f0 is 1, and so integrating 1, we get that big F0 is x. So big F0 is the function x, and we're plugging f inverse into the function x, which means this just comes out to be f inverse of x. So the base case is correct. Phi0 is in fact just the f inverse when we take it from this expression here. Now, we don't technically have to prove Phi1 now, but I'd like to show you that it does in fact work. So Phi1 would have to be two terms now, because we're adding from m equals 0 to n equals 1. And so this is going to be, starting off with m equals 0, we're going to have negative 1 to the power of 0, which is 1, and then x to the power of 1 minus 0, which is x, divided by 0 factorial over 1 factorial, which is both 1. And then we multiply by big F0 of f inverse, which we just saw is simply f inverse of x. And then we add negative 1 to the power of 1, which is negative 1, so we're going to get a negative symbol out the front. And then we're going to get x to the 1 minus 1, which is x to the 0, and that's again 1. We're going to get 1 factorial and 1 minus 1 factorial, so that's 1 factorial times 0 factorial, which is again all 1, and we're just going to get f sub 1 of f inverse of x. What is f sub 1, big F sub 1? Well, we know that the derivative of big F sub 1 is going to be f of x to the power of 1, which is just f of x. So that means that big F sub 1 is just the antiderivative of f of x, which is just the big F that we had in the original expression for the first integral of the inverse function. And so Phi1 is in fact the expression that we already know to be the answer there. So now what we should do is take the derivative of phi n and see that we do in fact get phi n minus 1. Phi n is precisely equal to the sum from m equals 0 to n of negative 1 to the power of m times x to the n minus m over m factorial times n minus m factorial times big F sub m of f inverse. But f inverse is Phi0, so I'm just going to write that from now on. Phi0 is f inverse. And the derivative of the inverse function is going to be, if integrating brings the index of phi up by 1, then differentiating should bring it down by 1. So the derivative of Phi0 should be phi negative 1, which we already know to be the derivative of f inverse of x, which we already know is 1 over f, the derivative of f composed with f inverse applied to x, right? We already know that that's the derivative of the inverse function. We're actually going to see this appear in our expression here, because we're going to differentiate this expression, and you'll see that we get the next phi down, phi n minus 1. So we take the derivative with respect to x, which means we have a function of x here, it's a power of x, and we have a function of x here because this is a function applied to the inverse, this is a function applied to f inverse of x. So this is a function of x and this is a function of x being multiplied together. That means the product rule. So what we're going to do is we're going to end up with two different terms when we do this. So we're taking the derivative of phi n with respect to x, and I'm doing a partial derivative because it's also a function of n, so I just want to make it clear that we're taking the derivative with respect to x. I guess n is seen as a discrete thing here, but we'll see some good examples of when it's not discrete, and it doesn't matter that we can take it to be any value we want. So we are taking the derivative, so we have the sum from m equals 0 to n, and now anything with only m and n and other numbers doesn't care about derivatives, so we just bring those out to the front. We get negative 1 to the m. We take the derivative of our x to the n minus m, so the power comes down, n minus m comes down, and then the power goes down by 1. So now I just write that as x to the n minus m minus 1, and that's all over m factorial times n minus m factorial, and then of course that's the derivative of the first thing, so we multiply by the second function, as is the product rule. And then of course the second thing is the next term in that, so everything, the first bit stays the same, so we have negative 1 to the m times x to the n minus m all over m factorial times n minus m factorial, and now we have to take the derivative of this. Well, we know the derivative of this expression of big F sub m is f of x to the power of m, but we know we're plugging in the inverse function, so we're plugging in Phi0, which is again f inverse. But then we have to multiply by the derivative of the inner function, which is the inverse function. And the derivative of the inverse function, we understand in our notation, is just phi negative 1. So Phi0 is the inverse of little f. Phi negative 1 is the derivative of the inverse of little f. Notice now we are applying f to f inverse, and we're raising that to the power of m. Well, f of f inverse is just x, right? Because those things are just canceling. And now we have x to the power of m. That's going to cancel with this x to the negative m right here. So x to the m goes away, and it goes away there. And we can just bring the phi, the derivative of the inverse of f right in there, phi negative 1. And now notice this first term is pretty much phi n minus 1 with this extra stuff tacked on. So we're going to separate these two things and see if we can't eke out our answer. So before we can actually assess if this is going to just give us phi n minus 1, we have to break up these two pieces and analyze them separately. So the first one, of course, can be written as the sum from m equals 0 to n of negative 1 to the power of m. And now you'll notice that this n minus m here in the numerator and this n minus m in the n minus m factorial are going to cancel each other. So I can just take x to the n minus m minus 1, rewrite it as x to the n minus 1 minus m. You'll see why I'm doing that in a moment. And I divide by m factorial, and of course the n minus m's cancel, so I now have n minus m minus 1 factorial. But I'm actually going to write that as n minus 1 minus m, like so. And that's, of course, being multiplied by big F sub m of f inverse. And then we have to tack on this little thing here, but when we tackle this one, I'm going to factor out everything that doesn't depend on m, so that we can simplify what's under the sum. So this is plus the sum. We have to what can we factor out? Well, x to the n doesn't depend on m in the sum, and the derivative of the inverse function doesn't depend on m either. So I can factor both of those out. I get x to the n times phi negative 1 times the sum from m equals 0 to n of negative 1 to the power of m divided by m factorial times n minus m factorial. Now, what I'm going to do here is I'm going to divide the outside by n factorial so that I can multiply the inside by n factorial, like that. And now we have a formula that we know. N factorial over m factorial, also over n minus m factorial, is n choose m. It's how many different ways you can choose m objects from n objects. So this becomes negative 1 to the power of m times n choose m. And what we should notice here is that if we plug in n, the last term of this sum here, we end up dividing by negative 1 factorial. Right? If you plug in n there, you get n minus 1, that comes out to negative 1. And negative 1 factorial is an undefined quantity. It's negative 1 is an infinite jump in the factorial function. It goes to positive and negative infinity, depending on which way you come at it from. But since the numerator is non-zero when we plug in n, when we plug in m equals n, and the denominator is blowing up to infinity in the limit, that means that that term is going to go to 0 in the limit, which means we don't need to include the nth term. We only have to go up to n minus 1. Now, what's really important to see here is that there's n minus 1 plugged into where we see n in our formula. There's n minus 1 plugged into where we see n plugged into our formula there. And there's n minus 1 plugged in where we see n there. Which means this thing right here is phi n minus 1. So if our job is done, then this better be 0. Now we know that x to the power of n over n factorial is not 0 in general. The derivative of our inverse functions can't be 0 in general, because that would mean that the inverse functions are constant. Then the original functions, f, would not be functions at all, so these two things can't be 0. That means that this thing has to be 0, and essentially what this is saying is it's an alternating sum over all of the binomial coefficients of degree n. So they go from 0 to n. And it turns out that this sum is in fact equal to 0, and so all of this goes away, and we are simply left with phi n minus 1. So that finally proves that our formula that we have is in fact correct. This does in fact give us a general formula for the integrals of the inverse functions of something in particular, of some particular function. We just need to know the inverse function of that function, and we need to know the antiderivative of each of the powers of the original function up to the nth power. Now, why is this useful? Well, it allows us to do some interesting stuff. What we should do is we should investigate the expression a little more and see if we can't transform it into something that might be easier to explore than this crazy stuff right here. So what we're going to do is we're going to do a similar thing that we did in the last step of our proof that this was the equation. We're going to factor out the things that do not depend on m. So we're going to factor out x to the n, and then we're going to again divide and multiply by n factorial. So I'm going to factor out x to the n, divide by n factorial, and that leaves us with the sum from m equals 0 to n times -1 over x to the m. And now that I've divided by n factorial, I have to multiply by n factorial inside, and again we're going to get n factorial over m factorial times n minus m factorial, which is the formula for n choose m. And then we multiply by big F sub m of phi 0, which is of course, again, this is the inverse of the original function little f of x, and this is the antiderivative of little f of x to the power of m, and that function is being applied to the inverse function. Now let's take out this 0th term here. So we're going to factor out, that should have been that right there. We're going to factor out -1 to the 0 over x to the power of 0 times n choose 0, big F sub 0 of phi 0. Right? All we did was just take out the 0th term there, and then we're going to add the rest of the sum. And we have the rest of the sum there, blah, blah, blah. So the rest of the stuff, blah, 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 blah. I don't want to rewrite it. So it's just every other term from 1 to n. But importantly, -1 to the 0 is 1, x to the 0 is 1, n choose 0 is 1, and the function, big F sub 0, is just the function x, and we are plugging f inverse into the function x, which means this whole expression here is again just the inverse of little f that we are calling phi. But that still leaves the rest of the sum left over. So we now have x to the n over n factorial times the inverse of f, phi 0, plus the sum from m equals 1 now to n of -1 to the power of m over x to the power of m times n choose m times big F sub m of phi 0. And what I'm going to do is I'm going to make that a minus sign and increase the power of -1 by 1 so that those things balance out. And what we're going to do now is we're going to assume that this expression, this sum, we're going to call it something new. We're going to call it j sub n of x, or maybe just j sub n for short. And this I like to call, just because it's a funny name, our junction function. I don't know why I call it this, other than the fact that it rhymes. I don't have a reason for it, but a junction function with respect to phi. Phi 0, I guess we could say. So it's a specific thing that's related to the function we're considering taking the inverses of. Maybe it's related to the original f, maybe it's related to the f inverse more closely. I'm not sure, but we have a couple of examples that I'd like to go over, and then perhaps other people can explore this a little bit farther. So in short, our phi n is now being expressed in this way. So it's x to the n over n factorial times phi 0, which is again the inverse of f, taking no integrals, minus this junction function jn. We're going to explore some of the properties of this much more compactified expression for the nth integral of the inverse of some function f. So let's take a look at this now, because we're going to derive an interesting differential equation from this. So we've shown that phi sub n can be expressed, the nth integral of some inverse function, phi 0. It can be expressed as x to the n over n factorial times that inverse function minus this new function, j sub n. But we also know that the derivative of phi n is phi n minus 1, right? That's part of the definition of what this thing is. Which means if I take the derivative of this expression here, I can relate it to phi sub n minus 1. So let's take the derivative. So the derivative of the first term is going to be, the n's going to come down and the power is going to go down by 1. So I'm going to have an n divided by n factorial. Well, that's just going to give me 1 over n minus 1 factorial. And so the derivative of the first part is x to the n minus 1 over n minus 1 factorial. And then, of course, we keep the second bit, which is the inverse function minus the junction function. And then we have to add the second bit. So we keep the first function, x to the n over n factorial. And now we have to take the derivative of these two things. The derivative of phi 0 is phi -1. And then we're going to have the partial derivative of the junction function, because again, it's also a function of n, so we just want to make sure we're being clear that this is a partial derivative. Now, why is this important? Well, we should keep going just to sort of express it a little bit better. We see that we have a common factor of x to the n minus 1 over n minus 1 factorial here, so we factor that out. The point of this is to try and make it look more like it's in this form here, so maybe we can make some statement about the pieces that are in either equation. So we factor out this term, we're left with phi 0 minus jn plus x over n, because that's what's left over after we've pulled all of this out of x to the n over n factorial, times phi negative 1 minus, again, the derivative with respect to x of the junction function. But notice, this is clearly, or very almost, in this form here. And this is phi n minus 1, so it better be in that form. But notice, and we have almost everything here, right? We have n minus 1 plugged into all of these places, except here, right? We want j n minus 1. Well, if I just factor out a negative 1 here, you see that we have to have j n minus 1, because this has to be it, right here. It can't be anything else, right? We took the derivative, we took the derivative of phi n, which is in this form, and we were able to rewrite that derivative, which is phi n minus 1, in that same form, x to the n minus 1 over n minus 1 factorial times phi 0 minus j sub n minus 1, then this has to be j sub n minus 1, which tells us we have this relationship here, that for any junction function of some inverse function phi 0, we can express this in this way, that the jn minus 1 is equal to jn minus x over n times phi negative 1 minus the derivative of the nth junction function at x. Doing some manipulation, subtracting that term over, dividing by negative 1, and multiplying both sides by n over x, you end up with the expression that n over x times j sub n minus j sub n minus 1 is precisely, and then you add that derivative over, you add the derivative of the nth junction function, and you end up with the derivative of the inverse function, phi sub negative 1, which is, of course, like I said, the derivative of the inverse function. The original inverse function, right? It's the derivative of that thing. So now we have this relationship here. We have that the derivative of our inverse function can be expressed in terms of this function here that we've seen in our thing. Remember, the junction function is that remaining big sum that was left over after we pulled out the inverse function from that sum. And so we can ask ourselves some interesting questions. What if this junction function is constant with respect to x? If this junction function is constant with respect to x, then this derivative would have to be 0, right? Because taking the derivative with respect to x would yield 0 if it was constant with respect to x, which tells us in that case that the derivative of our inverse function would have to be n times jn minus jn minus 1 all over x. But if the junction function is constant with respect to x, then jn and jn minus 1 must also be constant with respect to x, which means that the derivative of this particular inverse function is a constant divided by x, which tells us that this inverse function can only be this number, n times jn minus jn minus 1 times the natural logarithm of the absolute value of x. So the only functions that have a constant sum in their expression, so the only functions, phi, the only class of functions that are inverses that have this as a fixed value with respect to x are the logarithm functions. And if we wanted this to be a particular logarithm, where, right, we don't want, say we wanted our inverse to be just the logarithm, so this coefficient was 1, then we would need jn and jn minus 1 to differ by 1 over n, so they would cancel. But they have to differ by 1 over n, and we need jn to be 0 when we plug in n equals 0, because everything needs to go away and we just need to get phi 0 back. So if j0 needs to be 0, and each of the jn's needs to differ from the previous one by 1 over n, then that leaves only one option. That means for specifically the logarithm, if we let phi 0 be the logarithm of x, then that means that the nth integral of the logarithm of x has to be x to the n over n factorial times the logarithm of x minus this mysterious junction function. But we just said we know j of 0 has to be 0 for any junction function, so that it all simplifies down to a function we're talking about. But we also know here that jn minus jn minus 1 has to be 1 over n if we want it to cancel with that n from before. But the only function that satisfies j0 being 0 and the difference between the jn's being 1 over n is the nth harmonic number, right? Because the nth harmonic number is the sum of the first n reciprocals of the integers. But of course we also have a generalized way of expressing the nth harmonic number, as well as factorials and powers of x, which means we can talk about any integral of the natural logarithm of x. Except negative integer integrals, which would be the derivatives of the natural logarithm. For that, you'd have to do your own formula there, and of course that's just a formula involving repeated powers of negative powers of x, right? So this actually obscures the derivatives of the natural logarithm, but it opens up any other one that we want. Literally any number can be plugged in for n here, and we would get that integral of the logarithm. Just to show you that that actually is the case, let's plug in the logarithm into our general formula and see that we actually do get the harmonic numbers. So we have x to the n over n factorial times the natural logarithm of x minus the sum from m equals 1 to n of negative 1 to the power of m plus 1 over x to the m times n choose m times big F sub m of the natural logarithm of x. Well, what is big F sub m in this case? Well, this is the integral of the original function. So ln of x is the inverse function, so the original function must be e to the x. So we're saying that f sub m of x has to be the antiderivative of e to the mx dx, right? That's e to the x raised to the power of m. But of course this is simple. This is just e to the mx over m. But of course we're not talking about just f sub m of x, it's big F sub m of ln of x. So we're plugging ln of x into there, and when we do that, we get that big F sub m of ln x is simply x to the m over m, which means we take this and plug it into there, and we end up with x to the m over m there. But of course, this x to the m cancels with this x to the m. And now we are left with x to the n over n factorial times the natural logarithm of x minus the sum from m equals 1 to n of negative 1 to the power of m plus 1 over m times n choose m. And now, this will have to harken back to a much earlier video I did involving the harmonic series, where I proved that this series is in fact the nth harmonic number. And so it really does in fact work. This does actually give us the right answer, and this is the nth antiderivative of the natural logarithm of x. So I encourage you to plug in one of the continuous versions of the harmonic numbers that I've proven on this channel into Desmos, and then graph this function as a function of x, and then just do a slider for n, and you see that it smoothly transitions from the natural logarithm through all of its antiderivatives. So let's just check to make sure this works. We plug in 0, we get the natural logarithm of x back. I mean, that should be clear. X to the 0 over 0 factorial, that's 1. The 0th harmonic number is 0, so we just get ln of x. And if we plug in 1, we end up with x log x minus x if you FOIL everything out, and that is in fact the antiderivative of the natural logarithm of x. And so this just continues. But since we do have continuous versions of this, we can get a nice smooth transition between all of the antiderivatives, and the only ones that you can't see using this formula are the actual derivatives, the negative antiderivatives of natural logarithm of x, which you have to do using just taking repeated derivatives. Because the harmonic numbers are not defined at negative integers. And the next one I wanted to show you is what happens when we simply swap those things. So we're going to let f of x equal the natural logarithm of x, which means the inverse function is now e to the x. But we know that if we want to do repeated integrations of e to the x while ignoring the constant of integration, we're assuming it's always 0, then we know that at every step of the way we're just going to get e to the x. Which means I just need to transform this into the form of phi n, and we will definitely be guaranteed to get the junction function for e to the x. By that I mean we can multiply by x to the n over n factorial, and divide by x to the n over n factorial, which is of course the same as multiplying by n factorial over x to the n. We're still being multiplied by e to the x. And then I'm going to add and subtract e to the x on the inside, like so. But now I can rewrite this first, and then I can subtract e to the x. I can factor e to the x out of both of those things, and then I'm left with 1 minus n factorial over x to the n. We have to make sure that this is 0 when n is 0. Is it? Well, 0 factorial is 1 and x to the 0 is 1, so that fraction is going to be 1. 1 minus 1 is 0. So this is definitely the junction function for e to the x. So the function is e to the x times the quantity 1 minus n factorial over x to the n. But that means that this function here has to be equal to the sum from m equals 1 to n of negative 1 to the power of m plus 1 over x to the m times n choose m times big F sub m of, well, now we have to plug in the inverse function, so we're plugging in e to the x into that function. But of course, what is this? This is the antiderivative of the original function to the power of m. So we would have to know what the antiderivative of the natural logarithm to the power of m is. And as it turns out, this is simply the incomplete gamma function at m plus 1 negative log x. Since we are plugging in e to the x into this thing, the e to the x and the log x are going to cancel. We're just going to get negative x. So essentially we're taking this thing, plugging in e to the x into it, and that's what this part is here. So we're going to get gamma of m plus 1 comma negative x. Now what is this thing right here? The incomplete gamma function. We've seen this in my videos before. If we do gamma of s comma x is simply the integral from x to infinity of t to the s minus 1 times e to the negative t dt. So it's almost the gamma function. It goes to infinity in the upper bound, but we're not going all the way down to 0. So in this case, for this thing here, we would have m plus 1 plugged into here, so you would see t to the m, and then we'd have negative x plugged in down here. So that's just what's getting plugged into the function, and that's what this expression means right there. And what that means is that this sum, this strange-looking sum, has to be precisely equal to this function right here. It can't be anything else. So that's just another interesting example. And I think after those two examples, that's probably enough. And I look forward to seeing what other people might come up with for this repeated integrals of inverse functions. So thank you all for watching, and I hope this was an interesting little foray into my own little mathematical idea. Bye-bye now.